Hello everybody! Today in this video we are going to talk about sets and some notation that we're going to use in relation to sets. So let's start off with the definition of a set, and it is just a collection of unordered objects. For example, here I have a collection of erasers, so I have a set of erasers here, and if I have a subset, that means a set within the set, so I can say one of the subsets is just the hamster erasers. And if I wanted to denote a set on paper, meaning writing it down, I have to use the braces, the curly Q braces, to start and show the end of a set. And there are a lot of things that we can do with sets, and there's this whole thing called set theory, which we're not really going to go over. We're going to talk about a little bit, though, mainly the union and intersection of sets. Unions are the joining of all of the elements of two or more sets, and the intersection of the sets are the things that they have in common. So first off, I have an example of the set ABC union set AEIOU, and the resultant set of this is the combination of those two sets. So I have an A, a B, and a C, and then an E, an I, an O, and a U. And that set here is the union of those two sets. Now this upside down U stands for intersection, and it means what the two sets have in common. So if I want to find the intersection of those two sets, it's what they have in common, that overlapping section of a Venn diagram, and the resultant set is just A. Now if those two sets have nothing in common, then we need an empty set, which we can either denote by an empty set of curly Q braces, or we can use this symbol here, which is the symbol for the null set or the empty set. Now, when it comes to sets of numbers, they are infinitely huge and have properties and such, so we don't usually write them with the curly Q braces. We have symbols to denote them. And this is the hierarchy of the set of numbers that we deal with in Algebra 2, mainly the complex numbers. This C with a straight line through it denotes the complex numbers. Now we're not going to start off the year with complex numbers. Towards the end of the second 6 weeks, after we talk about matrices and things like that, we're going to talk about the complex numbers in the context of quadratics. And complex numbers are basically all the numbers that we're going to deal with. They can either be imaginary or real. You can't be both imaginary or real. You are either imaginary or real. And then, of course, this crazy R should be familiar from Algebra 1. It stands for the real numbers, and of which there are two types. There are the irrational ones, which are non-terminating, non-repeating decimals. And then we have the rational ones. And remember, rational comes from the word ratio. And by definition, rational numbers are numbers that can be expressed as the ratio of integers, meaning their decimals do terminate or repeat. And we use a Q for that. Now, in the irrational numbers, we have two types. We have the algebraic numbers, which are numbers created from radicals. Technically, they are numbers that are solutions to algebraic equations like polynomial equations. And then we have things that are called transcendental, which are not algebraic. For example, the most famous example of a transcendental number is pi, because it's not derived from a square root. Now going back to the rational numbers, this set here is like the middle school set of numbers, the ones you deal with in like 6th grade, 5th grade, and below. And we have integers and not integers. Of course, these are like fractions, like a half, a third, a fifth, whatever. And then integers, if you didn't know that, Z means integers. And of course, inside the integers, we have the natural numbers. And I say that they are the set of numbers that start 1, 2, 3, 4, 5, 6, 7, 8, 9. My computer scientist friend says it starts with 0, but as a mathematician, we say natural numbers start with 1. And then, of course, you have other things like digits and evens and odds and all other kind of stuff stuck within the integers, right? So these symbols are the symbols that we're going to use for those sets of numbers. Now, there are other useful symbols that you'll see. They are called quantifiers. And here are some quantifiers that you're going to see. This weird E means element of. So that says you want to show that something belongs to something. This upside down capital A stands for all. This backward capital E stands for there exists. Now, if I add an exclamation point, it's there exists a unique. So in quantifier language, that's not factorial or a really loud there exists. It stands for a unique. These three dots mean therefore. A comma and a big bar stands for such that. And when you see an arrow like this, it means then. Like, if you don't want to write the words if and then, you can just use that instead. So let me show you how these are going to be used. This is an example of a mathematical property written in the language of quantifiers. And I need you to translate it. Well, this means for all A, element real numbers. So that means for every single A that's a real number, this thing, remember, means there exists. So far we have for all A's that are real numbers, there exists. The opposite of A, comma, means such that A plus negative A equals 0. So this is the property that we're looking at, which is basically how opposites work, right? And this is all of the stuff that's like criteria for this property to be true. And this is how those quantifiers are going to be used. So if you look at a math book, really advanced math book, you're going to see lots of symbols like this.